My name is Vijay Garepalli, and my collaborator, Siddharth Samsi, are super excited to present on a data set that we've been collecting at MIT, and we hope that will be of incredible value to people who work in the area of machine learning, are looking to include or involve AI in optimizing their data center. So we're super excited to talk about this. A lot of this is a work in progress. And we are looking forward to hearing your feedback. Our contact information is later on in the presentation, and we would love to hear your thoughts on how we could make this data set more valuable and more applicable to a wider set of problems. This work has been supported through the MIT Air Force AI Accelerator, and both Sid and myself are from Lincoln Laboratory. I also wanted to especially acknowledge a few other folks. So David, Bester, Anson Cheng, Daniel Edelman, John Holodnak, and Balin Lee, who have been instrumental in developing this data set, amongst many others. So as I mentioned, there's a number of us at Lincoln Laboratory, and both Sid and myself are members of the Lincoln Laboratory Supercomputing Center, or LLSC. So the data set that we're collecting is thanks to everyone within the Lincoln Laboratory Supercomputing Center and a number of other folks across Lincoln Laboratory, MIT's Computer Science and AI Laboratory, Northeastern University, as well as the US Air Force. So thank you to all of these folks. So with that, I'm going to begin. I'll present a brief overview of our project and an overview of where our project fits in at MIT. I'll then hand things off to Sid, who's going to describe the data center challenge problem. We'll talk a lot about data and how we used a number of NVIDIA tools in order to collect some, I would say, pretty exciting data from our data center. And then he's going to talk about preliminary analysis and some of the potential questions that we're going to be releasing to the community of data center challenges. So as I mentioned, this work was done in collaboration with the US Air Force, and the US Air Force has made a substantial commitment at MIT in order to accelerate AI research. All of this fits into the umbrella of what's called the US Air Force MIT AI Accelerator, which has the end goal of bringing world-class research to Air Force missions. So the AI Accelerator brings together researchers from MIT campus, Lincoln Laboratory, as well as the Air Force. All of us are working on critical Air Force missions, such as computing in cyber, ISR and autonomy, or healthcare and disaster response. And we're doing this through developing mission-ready projects, which consist of foundational AI research, AI challenge problems, and education and training. So really, all of this combined is what forms the US Air Force MIT AI Accelerator. The AI Accelerator supports a number of projects at MIT, about 10 of them. And most of these projects, so if we look at the top 3 categories, tend to focus on algorithms and human-machine teaming aspects of it. The project that I help lead along with Sid is a systems-oriented project called Fast AI, and we're really focused on the fundamentals behind data and computing in order to make AI more applicable to a variety of problems. So today we'll be talking a lot more about one of the projects within this Fast AI project, but the overall AI accelerator brings together over 150 researchers across MIT and Lincoln Laboratory that are working closely with dozens of stakeholders and airmen across the US Air Force. As we all know, data is critical to breakthroughs in AI. And in this slide, all I've listed down here are a few breakthroughs in AI along with data sets and algorithms when they came out. While we may disagree on the exact dates and years of these breakthroughs, I think we'll all agree that data is critical to a breakthrough in AI. And so within this spirit and in the development of these type of data sets, through the US Air Force, we've been working to develop what we call challenge problems to enable these type of breakthroughs, but applied to problems of interest to the US Air Force. So in a typical research setting, we have a single team working on a single problem, and the probability of a breakthrough is often around 20%. And this is actually a pretty friendly or aggressive probability. Again, I want to note that this is the probability of a breakthrough and not good research. Good research happens all the time, but breakthroughs are something that are a little less common. Now, a program like the AI Accelerator, we have 10 different teams that are working on 10 different projects. And one would expect that given the same probability, that we'd see about 2 breakthroughs coming out of these 10 projects. Now, the goal behind this challenge is to take these 10 teams working on 10 problems, but to release 10 challenges that can then be worked on by hundreds of teams across the world in order to greatly improve the probability of a win or a breakthrough. And so, working on these challenges and developing these challenges and making them available to the community, we hope that there'll be tens of breakthroughs coming out of our Air Force Accelerator. Now, to be a little bit more specific, when we talk about an AI challenge, what does that mean and what does that include? So, an AI challenge will consist of a problem that is essentially a problem that can be solved using data. We will then release data sets. So, that could be either identifying data sets that are out there, or in our case, actually developing such a data set. We then work on data curation. So, this is converting the raw data into data that's useful and relevant to ML developers. And in our case, we even do anonymization of the data so that we can make this available publicly. We then make baseline algorithms available to people to really set the bar on what a baseline performance should look like. And we finally release a set of metrics that we can use to evaluate people who respond to our challenge. So within each of these are different deliverables that each of the projects that I mentioned earlier will be releasing. And so today, we're really going to be talking about how the Fast AI project is developing an AI challenge based on AI optimization of data centers. So with that, I'm going to hand things off to my colleague, Sid Samsi.
Thank you, Vijay. Good morning, everyone. So my name is Sid Samsi, and I'm going to talk about the data center challenge, how we collected our data, and some of the preliminary analysis and challenge questions that we're thinking about. So let me just start by first giving you a very high-level overview of the Fast AI project. The Fast AI project includes development along several technical thrusts, but the broad goal of this project is to develop new tools for rapid development and deployment of AI solutions. So within that sphere, within that umbrella, we have 4 parallel technical thrusts. The first 3 are high performance, swift development, and speedy deployment. And these primarily involve developing efficient parallel algorithms, data structures, high performance implementations for AI developers that they can use within AI environments that they're comfortable with and on supercomputers or cloud environments. The focus of today's talk is the 4th thrust, which is the challenge problem. And the idea behind the data center challenge problem is that complex systems need AI technologies to improve security, fault predictability, usage, and efficiency. So towards that end, the vision of the Fast AI Data Center Challenge is to foster innovation in AI approaches to the analysis of large-scale data center monitoring logs. Now, why data center logs? Well, data center monitoring offers a large variety of data streams and events. It's a rich data set that can act as a great surrogate for complex systems out in the real world. And so through this challenge, we want to develop AI challenges to enable prediction and early identification of system failures. So this could be trying to do a better job of early prediction of job failures, perhaps. Optimization of system scheduling with a view of improving resource consumption. Identification of optimization pathways for users' jobs. And last but not least, detection and stopping policy violations. So with that in mind, let me, before I can start describing our data set, let me just mention that there have been prior data center or cloud data sets that are available that are currently available, starting with the Google cluster data, which was released several years ago. The Atlas dataset that includes traces from a variety of workloads ranging from web services to high performance computing. The Philly traces data from Microsoft, which includes DN and training workloads. And last but not least, the Blue Water system monitoring data. which includes a wealth of information. And I would encourage you to go check out these sources also. But what makes our data set really unique is that we have a very rich set of time series data that, to our knowledge, is not currently available. And I'll be describing that through the rest of the talk here. So I'm going to talk now about our data collection methodology. Before I go into that, here's a quick overview of the MIT SuperCloud system. So the Lincoln Lab Supercomputer Center operates the MIT SuperCloud cluster. And our cluster is built to provide a software platform that allows interactive compute jobs, traditional HPC type jobs, and we also provide reference data sets that are pre-positioned in databases on the system, software module training, and so on. For more details, I encourage you to look up our details on our SuperCloud website. Now, what we're really excited about is in the middle of last year, we brought online our latest upgrade to our system, which is the TX Gaia, or Green AI Accelerator. This consists of almost 900 NVIDIA Volta GPUs with 32 gigabytes of RAM. So every node on the TX Gaia system has two NVIDIA Voltas. We are also in the process of adding more CPU-based resources, but we're really excited about trying to figure out how people are using these GPUs. Are there opportunities for improvement? Are there places where we can get better performance? And that's where monitoring systems are critical. Now, I'll just briefly mention the compute node and system architecture on each of our GPU nodes is as follows. We have two Intel Xeon Gold CPUs and two NVIDIA Voltas connected through a PCIe bus. We have two independent backend fabrics, a 100 gig Intel OmniPath and a 25 gig Ethernet connection. Each node has a terabyte of solid state drive and a 4 terabyte spinning drive locally. And we have a 3 petabyte cluster store array that is served up by the Lustre file system. So with that in mind, now we've been running a data center for over 10 years. And we already have a monitoring system in place that we've actually built into a little 3D game. And the best way to describe it, best way to show it is just through this demo. So you can see that we monitor everything from physical characteristics of the system to a system level view where you can see which users are on the system, how many jobs they're running, and so on. We also have this interactive usage where you can go click on a node, identify what host it is, get details on usage, what user is running. We can filter this information to find out a list of all the nodes that a user might be using currently. We can also look at the load on the system. So we can search for alerts such as excessive loads. So this system is great, but what we want to do is extend this system and make it even better than what it is today. So what are the types of data we're collecting? So let's start with the system level data. So this includes data that we can get from the Slurm scheduler. So this includes how many jobs are running or queued. We can filter this down to get a job breakdown by user or by resources, such as, is it a GPU job or is it a CPU job? And then what makes our data set really unique is the fact that we have CPU and GPU usage over time during the lifetime of a job and not just the summary statistics. So we feel that this is going to be critical in gaining new insights into workloads that are running on our systems. At the next level, for every job, we have information related to the user, the name of the job, the status of a job, and all the nodes that were assigned to it. At the hardware level, for every compute node, of course, we have the node name, but we are also collecting the number of processes running on that node. This is another way of looking at what's running on a node and compare it to what Slurm thinks something should be running on a node, and can help us identify anomalous behavior, such as a job spawning more threads than the number of cores they originally requested through Slurm. And finally, we have building management data, which includes electrical data and environmental data, humidity, temperature, and so on. So let's start by looking at these data sets one by one. But before we do that, let me speak a little bit about some of the considerations that we had to think about before we put in this data collection. So the first thing is that we wanted to record data from Slurm and NVIDIA's GPU monitoring tools on every node assigned to a job. Now, this meant writing out files for each of these monitoring tools. And so we were concerned about a potential impact on a job performance. Now, there may be thousands of simultaneously running jobs on the system, which in reality translates to potentially tens or hundreds of thousands of processes, and we want to monitor all of them. So if we start doing this data collection, we could potentially overwhelm the shared file system because of a massive number of concurrent file I/O operations. We also wanted to have the data collection be started and stopped automatically for each job with no user intervention. And lastly, we wanted to only collect GPU data for nodes that specifically requested a GPU, and not gratuitously just collect data that has essentially all zeros in it. So with this in mind, the data collection had to be transparent, lightweight, and should not affect data center operations. So what did we do? We decided to leverage Slurm's capabilities to enable this automated data collection. And the solutions were as follows. We used the Slurm job prologues to start the time series data collection. And this includes GPU monitoring using the NVIDIA SMI tool only if a job specifically requests a GPU, one or more GPUs. At the end of a job, we use the Slurm job epilogue to stop the collection of the data and then move the data from where it was being written on a local storage on each node, move it to central storage. And then finally, we also put in cron jobs that we used to extract the Slurm time series data from HDF5 files to CSV files. So the scheduler capabilities were leveraged heavily to enable this transparent data collection across the entire data center. So let's start looking at these data sets one by one. So the first is the Lustre data. Now, as we all, I'm sure everyone can agree here, shared file system is a critical component of the data center. The Lustre metadata server logs can provide important information about cluster-wide workload characteristics. For example, if we want to answer questions such as, were there an anomalous number of file open or file close operations over a given period of time, right? That could indicate that a certain job was misbehaving in the sense that perhaps the user wasn't aware that they were doing all these file I/O operations, which resulted in a slowdown of the system, not just for themselves but for everyone. Can we use this Lustre data to identify avenues for better planning of the file system usage, especially when we want to run expensive unlink operations? Similarly, could we link other expensive operations like get attribute, stat fs, set attribute, and so on to specific jobs? And you can see in the figure on the right here the list of system operations that we can get from Lustre metadata servers. And this is a rich source of information to identify why the system was unresponsive or some jobs took longer to run than they normally were expected to. So this would be a great data set for anomaly detection. The next is the node level data. The node level data is system data that we collect on every node independent of running jobs. So the data that Slurm collects for us is collected in the context of a running job, whereas this node data is independent of all of that. So we collect this data at every 5 minutes, And this includes the load average, memory usage on the node, the latency of the shared file system, the number of Lustre remote procedure calls, and more importantly, user IDs and the number of processes launched by each user on that node. Right now, you can see this in the figure on the right. I'm showing you anonymized data. So the first row is the node names, which are anonymized. The second one is the user PID count, which is the user ID, which is also anonymized, followed by the number of processes that a user has launched. Now, you can see how this would be useful in trying to diagnose the reason for maybe a system crash, or specific jobs, again, taking longer than they potentially would. Now, this could happen when maybe a third-party software launches way more parallel threads than the number of hardware cores that are available. So this can help us identify anomalous behavior, whether intentional or unintentional. So we can identify excessive load, which could be due to a bad job behavior. We could also identify potential file system issues. So for example, we have Lustre RPC totals, and we have a file system latency. We could use those to identify which nodes are taking longer to do file system operations, tie them back to individual users, and then further tie them back to individual jobs, and get a picture of what was happening before, say, a node failed or caused an issue for the file system. The next is the scheduler data. Now, the scheduler data provides an overview of jobs that ran on the system, right? So now this has identifiable data such as user IDs, job IDs, work directories, and so on. Now, what we've done is, as a first step, we've removed all the identifiable data that we think is not necessary for the analysis. For instance, the name of a job. We don't need to know the name of the job because that's more meaningful to the end user. Whereas user IDs, job IDs, node lists, these are things that we want to know when we go about analyzing the data. So these identifiable pieces of information have been completely anonymized, and to the best of our ability, I don't think you can reverse engineer those. And you can see some of these examples here. The third column shows ID underscore user, and you can see these values that are way beyond nominal values on a Linux system. And so this can give us a ton of information about trends on the system over time. Now let's start looking at the Slurm time series data. Now Slurm has the ability to gather time series data at a specified interval using the account gather profile or HDF5 plugin. And we collect this time series data on every node assigned to every job. Through a series of experiments, we decided that a 10-second interval was sufficient to identify interesting phenomenon. The metrics that are being collected include CPU details like the utilization and the frequency, the memory utilization by a job over time, and file IO in terms of megabytes written and megabytes read. To date, we've collected over 1 million time series in this manner, and we anticipate that a subset of this will be made available as part of the challenge. On the right here, I'm showing you examples of some of this data. The first row is megabytes read, and this is part of a job that I ran specifically to demonstrate this. And you can see I'm reading in a bunch of data on 4 nodes at the beginning of the job and not doing any data reads after. There's not much CPU utilization going on because the job that I ran was actually using GPUs for training a deep neural net. And you can also see the VM size, which is the memory, resident memory on the compute node through the lifetime of a job, and that remains through this particular job, and which remains fairly consistent throughout the life of the job as expected. So this is the kind of time series data you can expect. Now, what about the GPUs? Now, this is what we're really excited about. Like this, we're collecting GPU time series data again on every node assigned to a job that requests a GPU. So, for instance, if you have a 4-node job that requests 2 GPUs per node, you have data collected from 8 GPUs for that job. We're using the NVIDIA SMI utility to collect this data at 100 milliseconds interval. And you can see the list of metrics here: SM utilization, memory utilization, power usage, and GPU temperature, GPU and memory temperature. Now, to date, we've collected more than 25,000 GPU jobs. And again, we expect that we'll make a subset of this available. In the figure here, I'm showing you the time series data that I collected when using TensorFlow to train VGG16 on the ImageNet dataset on a single V100. Now you can see that the SM utilization has periodic spikes in it. Those basically also correspond to these spikes in GPU temperature and memory temperatures and the power draw. So we're very excited to see what we can gather, what new metrics we can collect out of this. And you can see that the memory usage is constant throughout the lifetime of the job. And for those that have used TensorFlow, you've probably seen similar phenomenon where TensorFlow allocates all the memory on the GPU during the lifetime of your training run, for example. So just a quick note on data availability. The data will be available through this website here, dcc.mit.edu, and we expect that the first release should be by early May of this year. And we plan to release 3 levels of data. The first level will be, this will be the smallest data set to be released, and it'll be a subset from a variety of AI ML workloads that are running known analyses. So it could be ImageNet, it could be VGG, Inception, ResNet, or other classification models being trained on ImageNet or other data sets with a variety of hyperparameters. So this will be a great data set that's appropriate for, say, characterizing specific workloads and potentially using as a ground truth. Level 2 data will be larger, and that'll include a variety of unknown workloads. So this could be ML workloads, this could be CFD, this could be pretty much anything that users are running on the system. Now, we will need to sign a data use agreement prior to getting access to the data. And then lastly, we have level 3 data, which is going to be the largest subset of the data that we're collecting. And that will be available on a case-by-case basis. And once again, you will need to sign a data use agreement. So let me now briefly talk about preliminary analysis and challenge questions. So just to be clear, this is a work in progress. We're actively collecting data and thinking about what kind of questions we want to ask. So what do we expect? So we expect to address one or more of the following potential analysis. The first is, can AI models do a better job of predicting runtimes? So if I'm sure many of you have used supercomputer centers before, and you know that in many, if not all cases, when you submit a job, you need to know approximately how long the job is going to run, so you can request resources for that amount of time. If you don't do a good job of estimating that time, your job could potentially be killed before it completes the analysis, thus wasting a lot of time. Now, if you're running in the cloud, wouldn't it be great to know approximately how much a job is going to cost you? For example, it's the meter's running, right? So can AI do a better job? Can we examine jobs that have run in the past and build a predictive model that gives you a good estimate of your job runtime based on what you run in the past? Now, can you use this time series data to develop AI-based tools to enable early prediction of job failures? Are there characteristics in these time series that'll tell you whether a job is going to start using an excessive amount of memory, is going to do excessive file I/O, is going to use too much CPU resources and slow everybody down? Could we develop tools to identify such behavior? Now, given a large number of anonymized data sets, could we also identify workloads that are similar to each other? And could we distinguish between AI machine learning jobs versus, say, a CFD job or any other kinds of compute? Finally, can we establish a baseline for workloads? right? So if we know what the baseline is, could we then use that to suggest optimization pathways for the user, or could we propose ways to schedule your jobs on hardware resources that are better suited for what you're actually going to compute? So this is by no means an exhaustive list, and we would love to hear any ideas that you have. So let me give you an example of an anomaly detection. So this was work done by my colleague, and without having access to the ground truth data, right? And the goal was to identify anomalies in about a year's worth of Slurm data. What we did was look at the number of users that submit jobs. And again, this is data extracted from the Slurm scheduler. So we computed distances between all pairs of subsequent windows of length k, and windows far from all others were considered anomalies. And lo and behold, we were actually able to identify this one event here highlighted in red. There was actually a 24-hour window that corresponded to an atypical cluster downtime. So we usually have a downtime once a month that lasts approximately a little under 24 hours. This one, because of factors beyond our control, was actually more than, it was about a 2-day downtime. And so even without ground truth, without knowing that this was this phenomenon was in the data, we were a colleague of ours was able to find this anomaly. So this was very exciting. Now the other thing that we're doing is because a lot of our workloads do tend to be deep neural network based, we want to try and characterize the training of deep neural networks on NVIDIA GPUs and try to see what pops out. So let's just start by looking at the file I/O first. Okay, this was a job that I ran on four compute nodes using 8 GPUs. Now you can see here the way I had structured the job. In the initial part of the job, I read in all my training data, right? And you can see that as spikes in the time series corresponding to the megabytes that are read. No other file read happens throughout the life of the job, and that's represented, and you can see that in the figure here. Now let's look at megabytes written, right? So again, the way I structured the job, at the end of an epoch, I save the model to disk. And you can see that in the spikes on the plot here. Now, node 4 was the only node that was supposed to save the model to disk at the end of an epoch. And you can see that in the red color spike in the plot here. So these correspond to end of model epoch save. So this is actually great data, right? Just looking at file I/O, we can start to identify phenomenology that could potentially help us identify certain aspects of deep neural network training. Next is the CPU utilization. There's not much CPU utilization because the CPU is just used to read the data into memory, maybe do some pre-processing, and just manage data transfers between the GPU and CPU and the file writes. So there's not much of interest going on there. And finally, if we look at the average SM utilization over the life of this job, you can see all GPUs were using about 20, utilization was about 20%, right? Not great, right? Which essentially tells us, hey, your utilization is this low, which means that there are potential avenues for, again, performance gain. So this probably means that the GPUs were data starved. So what this means is I could go back and change my model. I could increase my batch size potentially. I could start using more data to train these models, and I could squeeze more performance out of it and potentially train the same model on a larger data set for not too much more time. And so you can see how these time series can provide great important insights into job characteristics. Here's another example that we ran, and that was looking at GPU streaming multiprocessor utilization, or SM utilization, across the entire cluster. Now, the SM utilization, I'm sure folks already know this, indicates how much of the GPU cores are used by an application. And low utilization indicates that the GPU is underutilized and there's an opportunity for performance improvement. Now, what we found that a significant portion of jobs have zero SM utilization. This was not too surprising because we do have a contingent of users that don't use GPUs for their analysis. There are also situations where somebody might request a GPU, but they don't end up using it. And finally, there are lots of situations where you might request an interactive node, and you might request it for exclusive use. So when you request a compute node for exclusive use, you're essentially tying up those GPU resources regardless of whether you use them or not. So this was actually a great insight because that tells us that perhaps some of these folks that don't need a GPU but are tying them up anyway could use other hardware that doesn't have GPU so that the GPU jobs have more resources to run on. What we also found at the other end of the spectrum was that multi-GPU jobs, so jobs that use 5 to 8 GPUs, did a great job of using the GPU cores. And about 60% of them have at least 80% SM utilization. Now, this is also not surprising because if somebody is using multiple GPUs to run their jobs, it's highly likely that they're an expert user, they have experience in high performance computing, and they know how to optimize their code. But there's this gap between, say 20% utilization to 80% utilization, where if we see that there's a lot of room for improvement, right? So these might be codes that have significant room for performance improvement. There could be avenues where we could work with users on optimizing their jobs, or there could be other avenues such as use of newer compiler technologies to squeeze more performance out of the GPUs. So we're very excited about this data set because it's already starting to give us insights into our data center and our workloads on our system. So let me just summarize here. You're probably wondering at this point, how do I get involved? How do I get this data? So the data will be available at this URL here, dcc.mit.edu. We expect the first data release to be in early May. I'd say watch the website. Challenge problem specification and details of evaluation will be announced around September time, around the summer. And if you have any questions, if you have any suggestions, if you have ideas, if you want to be informed, please contact us at this email here, mit-dcc@mit.edu. And in summary, the data from MIT SuperCloud consists of complex and diverse data from schedulers, heterogeneous software, hardware, and networking and building management system. And these data can provide invaluable insight into the working of a data center to answer questions that can characterize such a complex system. And our goal through the Data Center Challenge is to use machine learning and artificial intelligence to potentially offer new insights into many aspects of the data center, such as system and workflow characterization, predictive modeling, smart scheduling, research optimization, and many, many more. So with that, this is the end of my talk, and we invite questions, comments, dcc.mit.edu website. Thank you very much.